Today, we're going to dig into a real workhorse of electronics, the Class B push-pull amplifier. We'll look at how it manages to crank out some serious power without being wasteful, and we'll explore the clever trade-offs that make it so incredibly useful.
Okay, so let's start with the big question, the one that every audio and power electronics engineer has to tackle. How do you get a really powerful signal without just burning up a ton of energy as heat? This is the core problem, and the Class B amplifier is a brilliant answer to it.
You know, the dream, the absolute goal for any amplifier is pretty simple. You take a small input signal, and you make a perfect, bigger version of it. You want more volume, more power, but you don't want to change its shape at all. It's all about purity and clean amplification.
But here's the catch. If you use just one Class B transistor, it's only active for half of the signal's journey, just 180 degrees of the wave. That means it only amplifies the positive part, or the negative part, but never both. And the result? It just chops the signal right in half. That's a massive amount of distortion, and it sounds terrible, not what we want at all.
So how on earth do we fix that? Well, with a really elegant idea called the push-pull solution. It's pretty logical when you think about it. If one transistor can only do half the work, why not just get two of them to work together as a team? And this is the heart of the design. In a push-pull setup, you've got two transistors that are basically partners in crime. One is set up to handle the entire positive half of the wave, we call that the push, and as soon as it's done, the other transistor jumps in to handle the entire negative half. That's the pull.
A really great way to picture this is to think of one of those old-school two-person saws for cutting logs. One person pushes, the other pulls. Neither one of them could do it alone, right? But because they're working together, back and forth, they create this perfectly smooth, continuous cut. That's exactly what's happening electronically inside this amplifier.
All right, so that's the concept. Now let's pop the hood and see what this actually looks like as a circuit. We're going to get into the nuts and bolts of how this thing really works.
So here it is, the schematic, and you can see our two main characters right in the center, transistors Q1 and Q2. Now, just as important are the transformers on the input and output. The input transformer is what splits the signal, sending one version to Q1 and an inverted version to Q2. Then, the output transformer's job is to stitch their work back together perfectly into one powerful wave. And here's how that teamwork plays out. When the input signal goes positive, Q1 kicks into gear, and Q2 is totally off. Then, the instant the signal swings negative, they switch roles. Q1 shuts down, and Q2 takes over. They are never, ever on at the same time. It's a perfect, coordinated handoff. So to break it down, first, Q1 builds the entire top half of the amplified wave. As the signal crosses zero, Q2 takes the baton and builds the entire bottom half. And finally, that output transformer does its magic, combining those two halves into a single, complete, and much more powerful signal that's ready to drive a speaker.
Okay, let's talk about the math behind the muscle. How much power are we actually getting? This formula here tells us the maximum possible AC output power. Vmax is just the peak voltage of our output signal, and RL is the load, like the resistance of your speaker. This number isn't just theory. It represents the real useful energy that's making the sound you hear.
Of course, to get that power out, you have to put power in. This second formula tells us how much DC power the whole circuit is pulling from your power supply. Here, VCC is the supply voltage, and Imax is the peak current the transistors draw. You can think of this as the total amount of fuel the engine is consuming to do its job.
And here is the big payoff. When you do the math, the maximum theoretical efficiency of a Class B amplifier is an incredible 78.5%. That's a huge number. It means that for every 100 watts of power you pull from the wall, more than 78 of those watts are turned into useful sound, not just wasted as heat. This is why this design is so popular. But as you probably know, in engineering, nothing is ever perfect. There's no free lunch. This super efficient design comes with its own very specific built-in flaw. Let's take a look at the one big catch.
And that flaw has a name: crossover distortion. It happens right at that zero crossing point, that critical moment where the signal crosses over from Q1 to Q2. See, transistors need a little bit of voltage, about 0.7 volts for a typical silicon one, just to wake up and start working. This creates a tiny little dead zone where both transistors are briefly off. And you can literally see the effect right here. The ideal output should be a perfect smooth wave. But if you look at the actual output from a Class B amp, you can see this little notch, a flat spot right in the middle where it crosses 0. That little gap is the signature of crossover distortion. So now we have the whole story. We've got the good and the bad. Let's lay it all out on the table and weigh the pros against the cons to figure out where this amplifier really belongs.
So on the plus side, you have that amazing efficiency, which means it runs cooler and is fantastic for high-power stuff. But on the minus side, you've got that annoying crossover distortion. Plus, the transformers can be big and expensive, and you really need your two transistors to be a perfectly matched pair. It's the classic engineering trade-off, power versus purity. So where do we actually see this design in the wild? Well, anywhere that high efficiency is the #1 priority. Think big, powerful concert audio amplifiers, radio transmitters that need to send signals over long distances, power inverters that convert DC to AC, and even the drivers for heavy-duty industrial motors. And this really brings us to the final key question that the Class B amplifier makes us ask. When is being incredibly efficient more important than being absolutely perfect? It's a great reminder that real-world engineering is all about picking the right set of compromises for the job. And in fact, it was this very question that pushed engineers to create the next step in the evolution, the Class AB amplifier, a design specifically made to get the best of both worlds.